Today to start with, we will look at some elementary results in vector calculus. The first one is Gauss divergence theorem. So, this states that a volume integral of the form del dot u dv can be written as a surface integral u dot n ds. Okay. It's in fact, it is a closed surface integral. So, if you have a certain volume V and the boundary of that volume is S, the outward normal is n, then this is what Gauss divergence theorem states. We are not going to prove it, we will just going to take it on fact, but the proof can be found in any book on vector calculus or some advanced engineering mathematics book. So, this theorem has got usage in, let us say, fluid mechanics and so many other places. We are going to use this theorem to prove what is known as Green's theorem in vector calculus. So, Green's theorem talks about the reduction of integrals of this form u del square v minus v del square u, and del square is the Laplacian. So, we are going to see how we can reduce this volume integral into a surface integral. So, towards that end, what we do is the following: we add del u dot del v and also subtract the same in this expression. So, we will add and subtract del u dot del v. Okay. That should be perfectly fine, but then this first integral would look like gradient of some quantity. So, if you look at del rather divergence of u del v is del u dot del v plus u del square v. Similarly, divergence of v del u is del u dot del v plus v del square u. This is u del square v. Okay. So, this is again just elementary rules of vector calculus, I am not proving it. So, using this identity, we can now reduce that volume integral into two divergences, del dot u del v minus del dot v del u, okay, dv. And now we know that each of these divergences can be put in the form of a surface integral using Gauss divergence theorem. So, these two volume integrals, which are divergence of some vector field, can be written in terms of two volume integrals, and the volume integrals each of these two divergence of volume integrals can be written as two surface integrals. The two surface integrals therefore, will be u del v dot n minus v del u dot n over the bounding surface, where n is the exterior normal. Okay. So, the moral of the story for Green's theorem is this: volume integral of u del square v minus v del square u dv has got to be surface integral of u del v minus v del u dot producted with the unit normal vector. Okay. So, this is Green's theorem, and we will use that in our study of Green's function. Okay. In the last class, we introduced the notion of Green's function. So, Green's function, it was said, is the solution to this differential equation here, that is, it is the inhomogeneous Helmholtz equation the inhomogeneity being in the form of a delta function centered at a specific point y, right. So, the solution of this equation was called the Green's function. So, we will take it up from there now. So, the solution of the inhomogeneous Helmholtz equation is the Green's function. Green's function is actually a very generic concept. For any partial differential equation with inhomogeneity, you can talk about its Green's function, but in the present course we are only dealing with the Helmholtz equation. So, this is the Green's function, more particularly of the Helmholtz equation. Okay. So, in particular we will have this condition, the Helmholtz function is designated as g x comma y or bar y plus k square g x bar y is equals to minus delta x minus y. So, this is the equation which the Green's function is supposed to satisfy, right. Remember, at this stage we are not talking about the boundary condition, but depending upon the domain of interest, the boundary condition could be virtually anything. So, the Green's function satisfies the above equation. The boundary condition of the Green's function is decided as per the domain of interest. What do I mean by that? Suppose I am interested in a domain which looks like this. So, if this is my V and if I know for sure that the pressure at the boundary is equals to 0, then what I will say that the Green's function will also satisfy this boundary condition. This is a finite volume problem. So, if for a certain finite volume problem we are sure that the volume that we are looking at terminates with a rigid boundary, then the corresponding Green's function will also satisfy the very same boundary condition, right. Similarly, sorry, this is p equals to 0, this is not velocity equals to 0, because the Green's function is after all a pressure like quantity, it is not a velocity like quantity, right. So, if similarly if you have any other arbitrary shaped quantity, arbitrary shaped volume, and therein you have a portion of the boundary wherein p equals to 0 and some other portion where v equals to 0. So, here we have let us say v equals to 0 and on the red hashed surface we have v equals to 0, sorry, p equals to 0, and then on some other portion somewhere here we have a certain impedance z that is specified. Then the corresponding Green's function will also have to necessarily have to satisfy these boundary conditions, that the Green's function itself must be 0 over the region where p is 0, because Green's function is a pressure like quantity. Similarly, if the normal velocities are 0, this I should say as normal velocity, it is not velocity at every direction, but normal velocity. So, if the normal velocity is 0, then the gradient of the Green's function along the direction of the normal should be 0, because del p dot n is the particle velocity along that normal direction. So, the moral of the story is this, that for finite volume cases, the Green's function satisfies either g x comma y equals to 0 in the region gamma p or SP, let us call this SP, wherein p equals to 0, right. So, this red region is SP where pressure has been specified. It will also satisfy gradient of g x comma y dot n equals to 0 in the region SV wherein V n equals to 0. This is the region where V n equals to 0, and in this region you must have the gradient of the Green's function dotted with the outward normal, which is something like this, that also should be 0. And in some other regions where it is only the impedance which is specified, neither the pressure nor the velocity, but it is the pressure by velocity ratio which gets specified due to the effect of an absorbing boundary conditions, let us say. So, therein again you will have this ratio which is g x y gradient g x y dot n could be specified in the region S z. So, this region I will call as S z, where the impedances are specified in the region where S z, where impedance is specified. So, that is the story as far as finite volume situations arise. The Green's function can be chosen to satisfy the exactly the same boundary conditions as is dictated by the domain of interest. But what happens for a infinite volume case? For an infinite volume case, as I said that in acoustics, exterior acoustics specifically, we would be interested in the volume which is the entire 3-dimensional space. So, for V which is equals to entire 3-dimensional space, and this type of problem generally occurs in exterior acoustics, where we are interested in the complete domain. There is no boundary that we wish to consider. Let us say we are talking about the acoustic radiation due to a submarine which is at the middle of the Pacific Ocean. So, therefore, it is virtually in an infinite medium. Similarly, we are talking about an aeroplane which is mid-air. So, we are talking again about an infinite medium. So, in that case, how do we specify the boundary condition associated with this domain and the corresponding Green's function? So, all that we will now call upon is the fact that what we have seen in our study of pulsating spheres and monopoles is that everything must reduce to plane wave situation, and plane wave situation demands that the pressure by velocity or the impedance should finally be rho c. So, that is the only thing which is there in our hand. So, somehow we want this quantity pressure by velocity along the radial direction should go to rho naught c, which is the plane wave impedance, but this should happen only as at large distances as r tends to infinity. So, at large distances the boundary condition that is demanded is for a complete infinite domain problem is that the pressure by velocity should go to rho naught c. But then you will realize there is also another condition that both pressure as well as the velocity will have a 1 by r decay. We have seen the 1 by r decay effect in the pressure. You could work out the 1 by r decay for the radial velocity also by appealing to the momentum equation. So, both P and u r has a 1 by r decay when we are talking about 3-dimensional acoustics. We have proved this from the point of view of monopole. Now, therefore, what we will say is that P by u r should approach rho naught c as r tends to 0. It should not only be equal, rather it should take the form as defined here. As r tends to infinity, P minus rho naught C u r should definitely be 0, but it is something more demanding than this. It will be 0 even if I multiply r. Why is that? Because both P and u r has a 1 by r dependence, that 1 by r dependence. So, this equality will be maintained at a rate which is faster than the linear then the this limiting condition will be attained at a rate which is commensurate with this 1 by r decay law. So, basically what I am saying is that this P and u r both fall as 1 by r, but the constant part associated with the P and u r, they will have a relationship, a scaling factor which is exactly rho naught C. So, this is the boundary condition associated with exterior acoustic, and this is called the Sommerfeld radiation condition. Okay. So, the Sommerfeld radiation condition is given mathematically by this, but this is just an intuitive proof that what is a Sommerfeld radiation condition. Basically, it is a condition which implies that far away from the source you should have the plane wave impedance getting satisfied, and the mathematical form of it also accommodates for the fact that both the pressure and the radial velocity has a 1 by r decay. So, that brings us to the Sommerfeld radiation condition. Another way of interpreting Sommerfeld radiation condition is this: the solution for the pressure which in fact satisfies the Sommerfeld radiation condition is in fact the outgoing solution. The incoming solution will not be able to satisfy this condition, because the incoming solution will demand a change of sign here. For the incoming situation you will have P plus rho naught C u r, but if you put it as P minus rho naught C u r, that means the radial velocity is directed outwards, right, which means it is an outgoing wave. So, satisfaction of the Sommerfeld radiation condition ensures only outgoing wave solutions. Incoming wave solutions do not satisfy the above condition. Okay. So, the Green's function which is in V equals to R 3 in the entire infinite domain, but satisfies the Sommerfeld's radiation condition as mentioned above, is supposed to be called as the free space Green's function. Free space means there are absolutely no boundaries. The space that is of interest is complete 3-dimensional space, nothing is excluded in that, but then the only exclusion principle that we apply is the principle that we are only going to look for outgoing waves, we are not going to look for incoming waves, and that seems physically obvious also, because incoming waves cannot arise in an infinite domain problem. Incoming waves only arise if there is a boundary, but in an infinite domain problem there is no boundary. So, there are no incoming waves. So, the Green's function in R 3 satisfying the Sommerfeld radiation condition is called the free space Green's function. Okay. So, please understand that there are many Green's function associated with every domain, you will get its Green's function. Associated with every domain and every boundary associated with that domain, you will get one incarnation of a Green's function associated with that specific domain and its boundary. Associated with the free space, when you are dealing with the domain which is as big as the complete 3 dimensional real space, that Green's function is called the free space Green's function, provided it additionally satisfies the Sommerfeld radiation condition, which essentially means you are looking for only the outgoing wave solution, the incoming wave solution is sort of filtered out. Okay. So, we are going to our next milestone would be to actually derive the form for this free space Green's function, and we will see that deriving this free space Green's function will be adequate for our purposes. So, towards that end we will make a few steps, but the first objective before we derive the form of that free space Green's function will be to study this very important effect of reciprocity. This is again something very intuitive, but can be rigorously proved mathematically also. So, what it says is that consider there is a certain source and there is a certain receiver. Green's function is after all the effect of the source on the receiver. That is, if you have a certain source at a certain point, then what is the reception at the point R. Now, the point is, if you flip the positions of the source and receiver, that means now you have receiver here and source there. The point is, will the by receiver I essentially mean a microphone or your human ear. So, if the position of the source and the receiver is interchanged, will there be any change in the signal that is received by your microphone or by your human ear? Obviously not, it only depends upon the distance, it does not depend upon the orientation or the locations, right. It only depends upon the relative distance. So, if me and you were to interchange our position, my sound would be appearing exactly the same. It will not change, it will not change provided it will not change whether I am in this recording studio or in the open air or in the playground, does not matter. In any domain, if the source and the receiver interchange their position, then the acoustic quantity or even any other signal quantity of interest will not change. That is essentially the principle of reciprocity. With that intuitive understanding, let us now look for little more formal understanding. So, what we are looking for is that the Green's function of y1 at y1 when the source is located at y2 must be the same as the Green's function at y2 when the source is located at y1. This is what we are required to prove. Okay. We will recall that the Green's function has this property, that is del square g x y1 plus k square g x y1 is minus delta x minus y1. This is exactly what we had for the Green's function rule. Here we have just replaced y with y1. Okay. Similarly, we also have del square g x y2 to be satisfying this equation, right. So, now what we will do is that we will multiply this equation with g x bar y2 and the other equation with g x bar y1. As a result, what we will get from the first equation, we will get g x bar y2 del square g x bar 1 plus k square g x bar y1 g x bar y2 equals to minus delta x minus y1 g x bar y2, right. And from the second equation, we will get g x bar y1 del square g x bar y2 plus k square g x bar y2 g x bar y1 equals to minus delta x minus y2 g x bar y1. And then what we will do is we will subtract these two, between these two equations we will do a subtraction operation, and as a result this second term will cancel out because they are identical. So, what we will have is the following: g x bar y2 del square g x bar y1 minus g x bar y1 del square g x bar y2 is equals to delta x minus y2 g x y1 minus delta x minus y1 g x bar y2, right, simple enough. And then finally, we will do a volume integral of these quantities. So, we will integrate both sides over the volume of interest, which is actually the entire 3-dimensional space. Sorry, in this 3-dimensional space, in the case that we are looking for an exterior acoustics problem, it could also be a finite dimensional space in which in case we are looking for a finite acoustic domain, right, it could be both. So, the reciprocity definitely holds for both exterior acoustic problems as well as interior acoustics problem. So, the volume could be anything at this stage. So, now what we will do in the next step is that we will use two very important results. Before stating that, let me just copy and paste this in the next page. Okay, so, having obtained this relationship, we will use two very important results again in mathematical in mathematics we have this very important result, which is the integration of a delta function with any function. So, integral of delta x minus x 0 f of x over any volume is supposed to be f of x 0, provided x 0 is within the volume of interest, right. So, this using this result, what we have for the right hand side of this equation is that we simply need to substitute in place of x the value of this shifted the shift in the delta function. So, that would read as g y 2 comma y 1 minus g y 1 comma or bar y 2. So, that is what is there in the right hand side of this equation. If you look at the left hand side of this equation, this is exactly in the form that is required by the Green's theorem. So, we will appeal to Green's theorem to reduce the volume integral into a surface integral, which is g x bar y 2 gradient of g x bar y 1 minus g x bar y 1 into gradient of g x bar y 2 dot n ds, and that must be equal to g y 2 by y 1 minus g y 1 by y 2. Okay. Now, the point is, as we said, that the principle of reciprocity demands that in fact, this left hand side, this surface integral should be 0, right, because g y 2 comma y 1 must be equals to g y 1 comma y 2 or bar y 2. So, to get to that effect, that why is this surface integral 0, we will recall that from momentum equation we have rho 0 del u del t, u is the particle velocity, is minus grad p, which means I omega rho 0 u in the normal direction, which is having a unit vector n, outward normal is having a unit vector n. So, u n will be minus grad p dot n, right. So, this is understood. Now, also for any volume of interest, whether finite or infinite, you have an impedance condition. If so, this is the volume of interest. So, if a certain portion of the boundary has pressure equals to 0, that essentially means impedance is 0. So, if P equals to 0, that means impedance is equals to 0. If we have u n to be equals to 0, that will imply that impedance is infinite, and in other cases, like in the case of 3D exterior acoustics problem, you will only have a specification of an impedance condition. P by u n equals to z is specified. So, the different boundary conditions that can arise in any acoustics problem for that matter, interior or exterior, boils down to a specification of the impedance condition. Both the Dirichlet and the Neumann boundary condition, which are basically pressure conditions or the normal velocity conditions, both of which are captured by the impedance boundary conditions. Not only that, there are some mixed boundary conditions problems which requires a specification of pressure by velocity, that ratio pressure by velocity gets specified, and therefore, we claim that any problem in acoustics, interior or exterior, involves a specification of the boundary condition in terms of impedance. In particular, I would like you to note that for the exterior acoustics problem, it is only an impedance boundary condition. The exterior acoustics problem finally specifies the Sommerfeld radiation condition as its boundary condition far away from the source, right. And the Sommerfeld radiation condition essentially is a specification of the impedance. The impedance at large distances away from the source basically boils down to the plane wave impedance, which is rho naught c. That is the moral of the story. So, therefore, the point is, for any volume of interest for a well posed acoustics problem, you must have on the boundary the value of the impedance specified, right, which means P by u n equals to z is specified for all points on the boundary. Okay. So, it is not necessary that on the boundary every point must have the same value of P by u n. It may be possible that some portions of the boundary will have certain so it may be possible that this portion of the boundary may be having a value of P by u n is equals to z 1, and in some other portions of the boundary it may be possible that you may have P by u n to be some other quantity z 2, depending upon what is the absorbing layer that has been put in the different regions, or in the worst case it could be one of them could be completely rigid. One of these walls, if it is completely rigid, then the associated impedance for that wall will go to infinite, right. But if some other walls is made of some perforated cardboard sheets, as you are seeing in this wall, then it will have its own impedance. So, therefore, the impedance need not be a constant value throughout the boundary, but the important point is there has to be a specification of P by u n, which could possibly depend upon the locations of the boundary, but none the same it has to be specified, right. So, the point is u n therefore, will be P by z x, z as a function of x, and u n in turn we have seen is given by, so u n here we have seen is given by gradient of p dot n divided by I omega rho 0. Okay. So, so here what I can do is I can put the I on the top, I times gradient of p dot n divided by omega by rho 0, minus 1 by I is plus I on the numerator. So, this is exactly what I will do. So, I times gradient of p dot n divided by z x is basically p. In other words, gradient of p dot n is z x, sorry I missed out the I omega rho 0, omega by rho 0. So, there is an omega by rho 0 here, right. U n is I delta p by n omega by rho 0. So, there is an omega by rho 0 here. Let us do this thing a little. So, this implies I omega I delta p dot n divided by omega rho 0, right, is equals to p by z x, right, which means delta p dot n is equals to omega rho 0 divided by I z x into p. In other words, gradient of p dot n is some quantity, I call it c of x times p, where c of x is omega rho 0 divided by I into z x. Okay. Z is the impedance. Now, this is what is true for pressure is also true for the Green's function, because Green's function is finally a pressure like quantity, right, that is the basic premise. So, therefore, this sort of a relation will also hold for the Green's function. So, delta g x comma y 1 dot n, n is the unit normal vector, is c of x g x bar y 1, and similarly gradient of g x bar y 2 dot n is also c of x g x bar y 2. So, this is how we related the two gradients in the I mean two directional derivatives in the normal direction of the Green's function with the value of the Green's function itself, right. So, now with this we turn back to this equation, which again I will copy and paste. So, we were left with this equation in our analysis. So, in our analysis we were left with this equation. Now, what we are doing is that we are simply going to replace gradient of g dot n to be the value of g multiplied by some constant which does change over the boundary, but we can keep track of that. So, this quantity will be g x comma y 2 into c of x g x comma y 1. So, what I have done is I have said that the gradient of g x, I have basically used this formula which I had derived, right. So, with that derivation I am led to the following: g x comma y 1, gradient of g x y 2 dot n is also c as a function of x into g x y 2, right, ds. Okay. So, this c possibly depends upon the boundary. So, I think better notation would be, instead of giving x, so this c depends on s, the location s, right. X is a is the point where we are receiving the acoustic signal. So, let us not use x. So, C, that constant which in turn depends upon the impedance, right, could vary from point to point on the boundary, that is the point. So, therefore, I will use a notation S, but anyway you can understand at this point that both of these terms in the surface integral are exactly the same, and therefore, this will vanish, which leads us to the crucial finding that the Green's function has the crucial reciprocity property, which I mean this basically turns out as 0, from where we get g y1 y2 is equals to g y2 y1. So, this is the reciprocity of Green's function proved in a mathematically rigorous fashion. However, you can have a very intuitive understanding, as I just said, that Green's function, the intuitive understanding of Green's function is that if there is a unit source, or if there is an impulse, if there is a source which is located at just one point, and you are interested to find what is the signal that is received because of a certain source at a certain point, then that signal is denoted by the Green's function, right. Obviously, the signal itself or the Green's function itself will depend upon the domain of interest, whether it is open playground, an open space, or a closed space. So, the Green's function does depend upon the properties of the domain that you are interested with. But no matter what be the domain, if simply the position of the source and the receiver is interchanged without affecting the strength of the source, then you can understand that the quality and the quantity of signal received at the receiver location, though the location has changed, it has swapped with the source location, the signal itself will not change, right. That is the idea of reciprocity, but none the same we have done the mathematical proof also. The reason why I did this mathematical proof is that exactly the same ideas will go through in the next proof, wherein we will derive the Kirchhoff-Helmholtz integral equation. So, that will sort of round things up, but the proof of Kirchhoff-Helmholtz integral equation will make use of the reciprocity, and it will proceed exactly along the same lines where we invoke Green's theorem, where we invoke properties of the delta function, and then once we look at Kirchhoff-Helmholtz integral equation, we will be able to set up the problem in 3-dimensional acoustics, which is basically the cornerstone of the numerical, I mean the equation itself may be too difficult to solve by pen and paper or analytical means. So, we will set things up so such that it can be done in a numerical fashion from there on, and that numerical technique is called the boundary element method, which obviously is not within the scope of this course, but none the same the basic point is that we will lead up to the formulation of the boundary element method, right. So, with that let us end the class here. We will see you again in the next class. Thank you.